Most people think of bacteria, they think bad, but the fact is most bacteria are good. Also, other microbes that are good are important ones like yeast, without which bread and beer would be impossible.
The question we had is, how could they do anything at all? I mean, they're incredibly small. You have to have a microscope to see one. They live this sort of boring life where they grow and divide, and they've always been considered to be these asocial reclusive organisms. And the clue to this came from another marine bacterium, and it's a bacterium called Vibrio fischeri. And this bacterium has the special property that it makes light. So it makes bioluminescence, like fireflies make light. And what was actually interesting to us was not that the bacteria made light, but when the bacteria made light. What we noticed is when the bacteria were alone, so when they were in dilute suspension, they made no light. But when they grew to a certain cell number, all the bacteria turned on light simultaneously. And so the question that we had is, how can bacteria, these primitive organisms, tell the difference from times when they're alone and times when they're in a community, and then all do something together? And what we figured out is that the way that they do that is that they talk to each other, and they talk with a chemical language.
Obviously, we communicate to each other in a variety of ways. We communicate with each other through verbal communication. There may be other communicating cues that that would allow people to communicate with each other. I mean, if I had bad breath, you'd want to sit far away from me, or that would be a communication on my part.
So this is now supposed to be my bacterial cell. When it's alone, it doesn't make any light. But what it does do is to make and secrete small molecules that you can think of like hormones. And these are the red triangles. And when the bacteria is alone, the molecules just float away, and so no light. But when the bacteria grow and double, and they're all participating in making these molecules, the extracellular amount of that molecule increases in proportion to cell number. And when the molecule hits a certain amount that tells the bacteria how many neighbors they are, they recognize that molecule, and all of the bacteria turn on light in synchrony. Vibrio fischeri lives in this squid. What you're looking at is the Hawaiian bobtail squid. And the reason the squid is willing to put up with these shenanigans is because it wants that light. And so the way that this symbiosis works is that this little squid lives just off the coast of Hawaii, so just in sort of shallow, knee-deep water. And the squid is nocturnal. So during the day, it buries itself in the sand and sleeps. But then at night, it has to come out to hunt. And so on bright nights, when there's lots of starlight or moonlight, that light can penetrate the depth of the water the squid lives in, since it's just in those couple feet of water. And what the squid has developed is a shutter that can open and close over this specialized light organ housing the bacteria. And then it has detectors on its back, so it can sense how much starlight or moonlight is hitting its back, and it opens and closes the shutter, so the amount of light coming out of the bottom, which is made by the bacterium, exactly matches how much light hits the squid's back. So the squid doesn't make a shadow. And so predators can't see its shadow, calculate its trajectory, and eat it. And so this is like the stealth bomber of the ocean.